Up until this time, all of the cell potential E0 values have been calculated assuming we were at standard conditions with concentrations of 1.00 molar. So what happens when we have concentrations that are different? Well, we have to adjust for non-standard conditions. And thinking back a few chapters to free energy, we said that the free energy G is equal to delta G0 under standard conditions plus RT times the natural log of Q, the ion product. And we remember that delta G was defined as minus NFE. So delta G0 is equal to minus NFE0. So we can substitute in. And when we do this, substituting negative NFE for delta G, we get minus NFE is equal to minus NFE0 plus RT times the natural log of Q. So if we rearrange this in combined terms, we end up with this. E, the cell potential, is equal to E0, the standard cell potential, minus 0.0592 volts divided by N, the number of moles of electrons, times the natural log of Q, the ion product. Now, why did I switch from natural log to the base 10 log? That's just kind of a historical chemistry perspective because chemistry is a very old science, and this was established a long time ago before it was easy to deal with natural logarithms because we have to get a natural log from a base 10 log. So, if we continue to substitute in, we get this. E is equal to E0 minus 0.0592 volts divided by N times the log of Q, and this is well defined and known as the Nernst equation. So this allows us to calculate the voltage at any time. And remember, N is the number of moles of electrons, and Q is the mass action expression. And we've been working with the ion product Q ever since we started equilibria in Chapter 15. So let's see how we use this in an application. Calculate the cell potential for a cell using these half reactions if the nickel-2 concentration is 1 times 10 to the negative fourth molar and the chromium-3 concentration is 2 times 10 to the negative third molar. Well, the first thing we do is to look at the chemistry. We have the nickel half cell and the chromium half cell. And if we look these up in the chart, for the nickel cell, my standard cell potential for that half reaction is negative 0.25 volts. And for the chromium cell, my standard cell potential is equal to negative 0.74 volts. If we hook these up, the way that these will react spontaneously is for the larger number, which is the nickel, to be the reduction half. So this will be the reduction, and this will be the oxidation. So my standard cell potential is equal to the E0 for the reduction minus E0 for the oxidation. So that's negative 0.25 volts minus a negative 0.74 volts. So my standard cell potential is equal to 0.49 volts. So we now have the E0 that we can use in this problem. Now, if we think about combining these two half reactions, we have 2 electrons here and 3 electrons in the chromium half. So we'd have to multiply the chromium half by 2 and the nickel half by 3. And that gives us 6 electrons in our overall chemistry. And then our N value will be equal to 6 moles of electrons. So we know the N, we know the E0. Now what we need is to find Q. So Q for this reaction comes from the combined reaction. And if we put these together, we get 3 nickel 2 plus, which is the reduction half, plus chromium solid, I'm turning that around because it's getting oxidized, is going to be in equilibrium with 3 nickel solid plus chromium 3 plus, and I have 2 of these, and my 6 electrons cancel. So now looking at this, I can see that when I ignore the solids in my ion expression, I get the concentration of the chromium ion squared divided by the concentration of the nickel ion, that's nickel 2, cubed. So I can go ahead and calculate my Q. My Q is equal to the chromium ion concentration, 2.0 times 10 to the negative third molar squared, divided by the nickel concentration, which is 1.0 times 10 to the negative fourth molar cubed. So that gives me a Q value of 4.0 times 10 to the sixth. Now, if you think about that, that's really large. That means that this is definitely product favored, so this is going to go forward and make lots of product. It is a spontaneous reaction. So now we can plug in to the Nernst equation. E is equal to E0 minus 0.0592 volts divided by N times the log of Q. So we go ahead and plug our numbers in. E is equal to E0, 0.49 volts, minus 0.0592 volts divided by 6 moles of electrons, times the log of 4.0 times 10 to the sixth. So E is equal to 0.49 volts minus 0.0652 volts. So my cell potential under these non-standard conditions is 0.42 volts. So in this case, we were solving for the potential, and we knew how we had made the cell. I'm going to have you try the next one on the next page. Go ahead and pause the video as you do this problem, then restart the video so that you can see the solution to this problem. So in this case, we already have the cell reaction, so we can start off with Q. We know Q is going to be the concentration of the zinc ion. This is balanced with a 1, so it'll just be to the first power, divided by the concentration of the copper ion, again to the first power. And we know the concentrations. My zinc concentration is 1 molar, and my copper concentration is 1 times 10 to the negative second molar. So my Q is equal to 100, and I can only keep 2 sig figs. If I look up my two half reactions, the copper reduction potential is 0.34 volts, and the zinc is negative 0.76 volts. That tells me that the copper will be the reduction half, and the zinc will be the oxidation half. And if I look at this, since I have a 2 plus charge on each, my N is equal to 2 moles of electrons. So now I can start by calculating my standard cell potential. E cell is equal to the reduction voltage, 0.34 volts, minus the oxidation voltage, a negative 0.76 volts, and that's equal to 1.10 volts for my E0. Now I can go ahead and plug into the Nernst equation. E is equal to E0, 1.10 volts, minus 0.0592 volts, divided by 2 moles of electrons, times the log of 100, with 2 sig figs. So that's equal to 1.10 volts, minus 0.0296, times 2.00. So my cell potential under non-standard conditions, E, is 1.10 volts minus 0.0592 volts. So my potential is 1.04 volts.